Hello, in this lecture we're going to talk about circular motion part 2, and we're going to start by discussing the difference between tangential and radial acceleration, and then we'll put them together to form total acceleration, which we also just called acceleration on its own, so that implies total. And then we'll do several practice problems so that we can reinforce all of these concepts. Alright, so we're going to start by talking about the difference between tangential velocity, tangential acceleration, and radial acceleration. Alright, so at any given moment in time, the instantaneous velocity of an object in circular motion is tangent to its circular path. So that means no matter where the object is, so let's say this object is going around and around in circles, and at this moment in time it's right here and it's traveling in a counterclockwise direction, then we would say its velocity is pointing in this direction, tangent to its path. Okay, so that's all that that's saying there. If it's moving in a uniform circular motion, that means that the velocity is changing because the direction is changing, but the speed is constant throughout. So that's why the length of each of these green vectors that you see here are all the same magnitude. So the velocity, we would say, is not constant because the velocity is a vector quantity which includes the speed and the direction. So the velocity is not constant since the direction keeps changing, but the speed itself would be constant because remember, speed is a scalar, doesn't include the direction, so the magnitude of each of those vectors are equal to each other. So the length of the vectors that are representing the speed of the object is constant as it's traveling around and around in that circular path, but since the direction keeps changing, we would say the velocity is not constant. So for objects that are moving in a circular motion, we defined angular acceleration as the rate at which the angular velocity changes with time. Okay, so when we talk about angular velocity, we're saying how fast is that angular velocity, so we're talking about the change in the angle over time. How fast is that changing over time? So we're talking about an acceleration now because it's radians per second would be the angular velocity, but how fast is that changing per second? So it would be radians per second, or radians per second squared. If an object is moving at a constant speed, then its angular velocity would be constant. Okay, because it would be traveling at the same speed, radians per second, and then per second it wouldn't be changing over time. So then that means that the angular velocity would be constant and the angular acceleration would be 0. Okay, remember the angular acceleration, which is alpha, is the change in angular velocity, which is omega, over time. So if the change in omega is 0, that's implying that the angular velocity is constant, right? There's no change, so that's 0. So then the whole thing becomes 0 over the time, which is just 0. So angular acceleration is 0 when you're in a uniform circular motion. And uniform circular motion just means you've got constant speed. Okay, so when we use the angular to linear conversion equation, which we discussed in a previous lecture, so the acceleration equals the angular acceleration times the radius, so this is the radius of that circular path. The a represents the acceleration of the object in the direction of its velocity. So this a, when we're talking about it in the equation, we can put a little subscript here to say it's the tangential acceleration. We don't need to put it in there. It's applied that that's the tangential acceleration, but that's what that means. So when we do a equals r times alpha, or alpha times r, doesn't matter which order you put those two in because you're multiplying them, that a is the acceleration in the direction of the velocity, so that means it's the acceleration in the tangential direction because we said the velocity is tangent to its circular path. So that acceleration is called the tangential acceleration. That acceleration is telling you how fast is the object speeding up or slowing down. Okay? So if it's moving at a constant speed, then it would be 0. That acceleration would be 0. Okay, so this acceleration is called tangential acceleration. If you use one of the linear kinematic equations for an object traveling in circular motion, the A, okay, the A in the kinematic equations that you're using, that's representing the tangential acceleration. So if an object is moving in uniform motion, so it's at a constant speed, then the tangential acceleration we said was 0, right? Because we talked about it over here. If you're in uniform circular motion, then your omega, your angular velocity, is constant, because you would be moving, let's say you're moving at pi radians every second, pi radians per second, and it keeps, your omega is constant, so pi radians per second here, here, and here is still the same angular velocity, pi radians every second. That's not changing. So the delta omega, which is the change in the omega, is 0, because the omega initial, we're saying, for example, is pi radians per second, and the omega final is also the same value, pi radians per second, as just an example. And so the change in omega is the final omega minus the initial, which is just 0. So if you're moving at a constant speed in the circular path, your omega will be constant, and so your alpha will be 0. Okay, so that's the key piece of information here. Using this equation, V final equals V initial plus A delta t, over here, we can say that the acceleration of an object, if we rearrange and solve for A, we're bringing the V initial to the other side of the equation and dividing both sides by delta t, we get A equals V final minus V initial over delta t. Although an object that is traveling in uniform circular motion has a constant speed, okay, so uniform circular motion means the speed is constant. We mentioned earlier that doesn't mean that the velocity is constant too, because it's traveling in a circular path. Even though the speed is constant, its direction keeps changing as it keeps traveling along that circle. So if it's changing its velocity, if it's changing the direction, then its velocity can't be constant, because velocity includes direction. So its velocity changes as its direction changes. Thus, it has to be accelerating. Remember, acceleration is the change in velocity over the change in time. So if our velocity is changing, then that means that our acceleration has to be non-zero. So it is a value. So it's accelerating. To determine the direction of the acceleration, we can think about the instantaneous velocity vectors and figure out what V final minus V initial is. Okay, so let's think about what is the direction of this acceleration vector if you're traveling in uniform circular motion. So that means constant speed, but around a circular path. So let's say at one moment in time, your velocity looks like this. So I'll say this is V initial, and that at another moment in time, your velocity looks like this. Looks like this. So this is V final. Okay, so now if we were to do V final minus V initial, remember we're using this equation. Acceleration is equal to V final minus V initial over delta t. So let's figure out, what does V final minus V initial look like? Well, V final is the second vector that I drew, and when we minus V initial, I will draw that in a different color. So V initial is pointing one direction. Minusing V initial from V final means you're just making V initial point in the opposite direction. So it's kind of like this. So this is minus V initial, right? V initial is going in one direction. Negative V initial would just go in the opposite direction. And when you're adding vectors, you want to add them so they're tip to tail. So I slid the V initial over so that its tail touches the tip of V final. So I'm doing V final minus V initial, which is the same thing as saying V final plus negative V initial. So I have my first vector, the blue one, V final, plus my negative v initial vector. And what does that give us? A vector that looks like this. So this vector over here is v final minus v initial. Okay, then when we take that and we divide it by delta t, well, delta t is a scalar. It doesn't have a direction to it. So when we divide that by a number, it just changes the length of this vector, but the direction of it would still be going in the same, it would still have the same direction. So what is the direction that it's pointing in? You can see v final minus v initial will point towards the center of the circle, right? So it's pointing towards the center. So that's what's really important to know, that if an object is traveling in a circle path, it will always have a radial acceleration which points towards the center of the circle. And that is really important. So we have two ideas that are happening so far right now. What we said was, if the object is moving in a uniform motion, that means constant speed, then that means it doesn't have a tangential acceleration. So there's no tangential acceleration. Tangential acceleration is only going to exist if your object is either speeding up or slowing down. But if your object is traveling in a circular path, then that means it has to have radial acceleration, and that radial acceleration always points towards the center of the circular path. Okay, there's two formulas that you can use to calculate the radial acceleration. We have AR equals v squared over r, and if you like, you can refer to this little video here that shows how that formula is derived. And you can use this second equation, AR equals omega squared r. Those are actually the exact same equation. So remember, we had the linear to angular conversion. It was v equals omega r. Well, if we looked at our first equation, AR equals v squared over r, and let's say we said, okay, I'm going to substitute omega r in for my v over here, since v equals omega r. So I'll replace my v with omega r. It's all squared divided by r. And what do I get? Omega squared r squared over r. One of my r's cancels out, and I get omega squared r, which is the same as the equation over here. So those two equations are exactly the same. You just decide which one you use based on what information you know. If you know the velocity of the object, then you would use the first equation. If you know the angular velocity, you'd use the second equation. Okay? All right, next I'm going to introduce total acceleration. An object that is traveling with a changing speed will have what type of acceleration? So what did we talk about in the previous slide? If the speed keeps changing, then that means that it's going to have a tangential acceleration. Okay, so tangential acceleration is similar to the acceleration you're already used to from previous lectures. So it's just talking about if your speed is changing, you're going to have an acceleration. That's called tangential acceleration. It doesn't have anything to do with the fact that you're traveling in a circular path. Okay, so if you're driving your car at 10 kilometers per hour and then you accelerate to 30 kilometers per hour, then that would be referred to as tangential acceleration. You don't need to use the word tangential, it's just implied that that's your tangential acceleration. Okay, the direction of that acceleration is tangent to the circular path. Okay, so that's what we talked about in the previous slide. So if you're traveling in a circular path, let's say you're going in this counterclockwise direction, and at this moment in time you're right here, then your tangential velocity would be traveling that way. But if you are speeding up or slowing down, if you were speeding up, then your acceleration, your tangential acceleration would point in the same direction that you're moving. And if you're slowing down, then your tangential acceleration would point in the opposite direction that you're moving. Okay, so this is only happening if you are speeding up or slowing down. An object that's traveling in a circular path will have radial acceleration. So this is that other type of acceleration we were talking about. We said radial acceleration always points, remember when we did v final minus v initial? Let's say this is v initial. V final minus v initial. This is minus v initial here. We end up getting this vector, v final minus of v initial, which always points towards the center of the circular path. Okay, so there's two types of acceleration now. So we have tangential acceleration. That's the type of acceleration you get when your object is speeding up or slowing down. If it's speeding up, the tangential direction is pointing in the same direction that the object is moving, just like if you were traveling in a straight line. If you're slowing down, then the tangential acceleration is traveling in the opposite direction, or it's pointing in the opposite direction of your motion, just like it would be if you were traveling in a straight line. But if you're traveling in a circular path, then no matter what, you're also going to have radial acceleration. And radial acceleration always points towards the center of the circular path. Okay, so if a question asks you to determine the acceleration of an object, and it doesn't say which type, you have to find both the tangential and the radial acceleration and then add them together as vectors. Okay, so if you have a question that asks for acceleration, you have to ask yourself two questions. First, is the object's speed changing? If the object's speed is changing, then it's going to have tangential acceleration. You can use one of the kinematic equations to figure out what the tangential acceleration is, because remember, in the kinematic equations, all those A's that you see, those are referring to tangential accelerations. The second thing you ask yourself is the object moving in a circular path? If it is, it will automatically have radial acceleration. Okay, and there are equations to figure out what the radial acceleration is. So remember, we said AR is equal to V squared over R, or AR is equal to omega squared R. Those are the two ways to figure out what the radial acceleration is. Whereas the tangential acceleration is from the kinematic equations. Okay, so all the accelerations in the kinematic equations, those are referring to the tangential acceleration. Okay, so the acceleration in the kinematic equations are equal to tangential. They just normally don't put tangential in there because normally kinematic equations are referring to objects that are moving in a linear fashion, and so the tangential acceleration is just implied. If you're traveling in this direction, then of course the direction of your velocity is also going in this direction, and that is tangent to the line that you drew, but it's a straight line, so it's the line itself. Whereas if you're traveling in a circular path, a tangent line would look like this, and that's the direction of your velocity at any given moment in time. And if that velocity is changing, then that would be the direction of your tangential acceleration as well. If it's speeding up, or if it was slowing down, the tangential acceleration would go in the opposite direction. Okay, so let's look at this summary of equations here. So first, we have the linear to circular conversions. So we have S, which is your displacement, is equal to R times theta, or you can think of it as your position, is R times your angular position. V, your velocity, is equal to R times your angular velocity. And A, your acceleration, is equal to R times alpha. Now I put a little t there because that's your tangential acceleration. Okay, so this is A and this is alpha. They look very similar to each other, but the alpha looks more like this. Okay, kind of like a fish. Okay, and then in the last equation, we have how do you calculate AR? So that's what we were mentioning earlier up here. Okay, so the two equations, AR equals V squared over R, or AR equals omega squared R. Okay, then we have the three kinematic equations that we discussed earlier on in the course, and then we have the circular version of them. So all of the S's can change to thetas, all of the V's change to omegas, the A's change to alphas. Okay, so we have the same equations, but just written in circular form. So let's do some practice problems. Okay, number one, a discus thrower rotates a 1 kilogram disc along a circular path of radius 1.06 meters. The maximum speed of the discus is 20 meters per second. Determine the magnitude of the maximum radial acceleration of the discus. Okay, and the answer is just given there just for your convenience. So the discus thrower rotates. The mass of the discus is 1 kilogram. I'm just going to write down everything that we know. The radius of the circular path is 1.06 meters. The maximum speed of the discus, so this is V, I'll write max, is 20. It's in meters per second, so that's why I'm writing V. It's not an angular velocity, it's a linear velocity. Determine the magnitude of the maximum radial acceleration of the discus. So I'm looking for the acceleration, radial, and the maximum. Okay, so we have to think about, well, what equation can we use to find radial acceleration? Well, remember we have two equations for radial acceleration. AR equals V squared over R, or AR equals omega squared R. So just depending on what you're given in the question, which equation should we use here? Well, we know V, we don't know omega. So we're going to use the first equation. AR equals V squared over R. We're looking for the maximum radial acceleration, which means we need to use the maximum velocity, the maximum speed. So I'm going to use this 20 meters per second. Okay, so I'm looking for my maximum radial acceleration, so I'm going to put in my maximum speed. So my maximum speed is 20 meters per second. I'm going to square that for the equation. So 20 squared over R, which is 1.06. So notice that the mass of the discus really didn't make any difference. We didn't use it in the equation at all. So I'm going to just type this on my calculator, 20 squared over 1.06, and I get 377 meters per second squared. Okay, as far as decimal places, really we should only have 3 significant figures here because the question, all the numbers only have 3 significant figures. On a test though, I might say at the beginning of the test to round everything to 2 decimal places unless noted otherwise in the question. Okay, question 2. A tire with a radius of, so I'm going to write down what we know. The radius is 0.5 meters. Rotates at a constant rate of 200 RPM. So what variable is this? Revolutions per minute. This is our omega, but the units are a little bit different. 200 revolutions per minute. Remember, the units for omega should be radians per second, so we just need to convert our units. So I'll convert revolutions, so I'm going to put it in the denominator so it cancels out. Instead, we want radians. And 1 revolution is the same as 2 pi radians. Now we want to get rid of minutes as well, so we're going to put minutes in the numerator so that it cancels out with the seconds, with the minutes that are down here. And then instead we have 60 seconds, because 1 minute is the same as 60 seconds. So I can type this up, 200 times 2 pi divided by 60. And I get 20 pi over 3. This isn't my final answer, so I'm just going to leave this like this so that it's more exact rather than putting in a decimal. You can put in, enter in a decimal if you like, but I would keep extra digits, and this is just more exact. So the question says, find the speed and the acceleration of a small stone lodged in the tread of the tire, so on its outer edge. So let's start off with the speed. So speed is V, and my equation for speed, when I know the angular velocity and the radius, would just be V equals omega R. Okay, so my omega is 20 pi over 3, and my R is just the radius of that tire because the stone is lodged on the outside edge of the tire. So if this is my tire, the stone is right on the outside edge. So the radius of the circular path that the stone travels is just the radius of that tire. So 0.5 meters. And so when I type that up, I get 10.47, or rounded, I'll say 10.5 meters per second. So that's my speed, and I also want the acceleration. Okay, so what type of acceleration is this? So when it asks for acceleration, you always have to ask yourself, is this tangential, Does it have radial, or do we have to put both of them together? Okay, so let's think about it. Tangential acceleration. We said the object will have tangential acceleration if the speed is changing. So if it's either speeding up or slowing down. Is this object, the stone that's lodged on the tread of the tire, is its speed changing? Well, it tells you that the tire is rotating at a constant rate. So constant rate means the speed is constant, right? So constant speed. Therefore, tangential acceleration is 0. Okay, it's like you're walking along the street and you're walking at a constant speed. You're not accelerating. That's referring to the tangential acceleration. Okay, but the fact that it's traveling in a circular path means that there is some type of acceleration here. And that would be radial acceleration. Okay, so it does not equal 0 because it's traveling in a circular path. So there is a radial acceleration. And remember, there's 2 formulas for radial acceleration. And here we know what the v is because we just found it, and we also know what the omega is because we have that from before. So we can use either of the 2 equations. The v has some rounding errors, so if we're going to use that v, we should really put in all the digits. So all of the digits were 10.47198. They keep going, but just having some extra would be good to put in. So we could do that. We can say v squared, which is 10.47198 squared over r, 0.5. Or we can use this equation, omega squared, which is 20 pi over 3 squared times r. And either way, we should get the exact same answer. So I'm going to type it up on my calculator. And I get 219 meters per second squared. And in this other case, I have 2 pi over 3 squared times 0.5, and I get the same answer. Sorry, it was 20 pi over 3 times 0.5, and I still get 219 meters per second. So see, it doesn't matter which equation I use, since in this case we have both the v and the omega. Okay, so the question said find the speed. So the speed was 10.5 meters per second, and find the acceleration. Well, the acceleration, there's only a radial acceleration, there's no tangential, so our total acceleration is just the radial acceleration, which is 219 meters per second squared, and the direction of that is towards the center of the circle. Or if you don't want to write all those words, you can just say inward. Okay? All right, let's move on to another question. Number 3. The astronaut orbiting the Earth is preparing to dock with a satellite. The satellite is in a circular orbit 600 kilometers above the Earth's surface, where the free fall acceleration is 8.21 meters per second squared. Take the radius of the Earth as 6,400 kilometers. Determine the speed of the satellite and the time interval required to complete one orbit in minutes. Okay, let's draw a picture of what's happening. So we've got the Earth here. So I'm just going to draw the Earth. And it tells you that the radius of the Earth is 6,400 kilometers. But that's in kilometers. We should really change the units. So if we do 6,400 kilometers, and we want to change the units, I'm going to get rid of kilometers. 1 kilometer is 1,000 meters. I get 6,400,000 meters. Or another way of writing that is 6.4 times 10 to the 1, 2, 3, 4, 5, 6 meters. Okay, so that's this radius here. But then it says that an astronaut is 600 kilometers above the Earth's surface. So 600 kilometers, let's say that's somewhere over here. So this is another 600 kilometers. 600 kilometers. Again, it's not in the correct SI unit, so I'm going to change it. 1 kilometer is 1,000 meters. Kilometers cancels out, and I'm left with 600,000 meters, which is 6 times 10 to the 5 meters. So that's what this is, 6 times 10 to the 5 meters. Okay, so I have 6.4 million meters and 600,000 meters. All right, so it tells us that the free fall acceleration is 8.21 meters per second squared. Now what we need to do is think about what type of acceleration is that. We've talked about different types. So it's either a tangential acceleration or a radial acceleration. So what is that when they're talking about free fall acceleration? So think about that when we talk about our acceleration due to gravity, and that's what they're referring to, but we're at a higher altitude now. We're in orbit, so we're 600 kilometers above the Earth. So that acceleration is not 9.81 anymore, it's 8.21 because we're far away from the surface of the Earth. So if we were talking about any acceleration due to gravity, whether we're far away or close to the surface of the Earth, which direction is it pointed? So say we're on the Earth right now and we're on the surface of the Earth, which way does gravity always point? Well, we always say it always points downwards. What we really mean is it always points towards the center of the Earth. It always points towards the center of the object that's pulling us towards it. So in the case of us on the Earth, or an object towards near the surface of the Earth, it's pulling us down, right? To us it's down, but really it's going towards the center of the Earth. And so what type of acceleration points towards the center of the circular path? That would be the radial acceleration. So this is the radial acceleration here. It says the free fall acceleration is 8.21 meters per second squared. That is the radial acceleration. It points towards the center of the circular path. When we're talking about this astronaut that's in orbit, right? So this astronaut right here, its acceleration, free fall acceleration, is pointing downwards, right? Towards the center of the Earth. That's its radial acceleration. So we know the radial acceleration is 8.21 meters per second squared. We're going to need to know what the radius is of the astronaut's circular path. The radius is not just its altitude, but it's the distance from the object to the center of the circular path. So it would be this full distance like that. So we'd have to add those two distances up. So we'd have to add the radius of the Earth, 6.4 times 10 to the 6, plus 6 times 10 to the 5. And so that gives us 7 times 10 to the 6 meters. So that's the radius. Okay, so then the question is asking, determine the speed of the satellite. So it's asking for v. So when it comes to radial acceleration, we only have two choices with equations, v squared over r, or ar equals omega squared r. This question's asking us for v, so we're going to use the first equation on the left. So our ar, we know what it is, we know what our r is, and we're solving for our v. So let's just rearrange the equation. We have v squared equals ar times r, if we cross multiply. And then when we solve for v, we get square root of ar times r. So we can put in our numbers. Ar is 8.21, and r is 7 times 10 to the 6. All in a square root sign. So I'm just going to type this up. 8.21 times 7 times 10 to the 6, and I get 7580. Well, 7581, but then if I'm rounding to how many significant digits? So we have 3 over here, 4 over here, and 1, 2, 3, 4, 5 over here. So our answer should have 3 because it should be the fewest of all the numbers that are given. So even though it's 7581, we should be rounding so it only has 3, so we're going to make that last digit a 0 so that it's not significant. And then we have meters per second here. Okay, so that's the first part where it says what is the speed of the satellite. The next thing is what is the time interval required to complete one orbit. So the time to complete one orbit is the same as saying what is the period. And we can figure this out by first finding the omega. Okay, so let's see what happens. So we know the V and we know the R, so we should be able to figure out the omega. So we have this equation, V equals omega R. So to get the omega, it equals V over R. So I have my V, and I'm going to put in more digits this time, 7580.897 over R, and our R is 7 times 10 to the 6. Okay, so I'm going to type this up. And I get 1.08299 times 10 to the negative 3. So what are the units for this? This is omega. So omega is radians per second. Now what's the question asking? It wants to know what is the time interval required to complete one orbit. So it wants to know how much time does it take to complete one orbit. So that's called a period. So I'm going to do this work on the side now, the rest of this. So my period is equal to, so I want to know how much time to complete an orbit. So instead of putting the number 1.08299 times 10 to the negative 3 radians in the numerator, I want to put it in the denominator, 1.08299 times 10 to the negative 3 radians, and the seconds in the numerator. So it looks kind of strange. So what I'm doing is I'm trying to find out how much time it takes to complete one cycle. So I'm going to start off by changing this to be seconds per cycle. The question specifically asks for it to be in minutes, so once I get seconds, I'm going to change it to minutes. But I just flipped around this fraction basically. See, I turned this into a big fraction and I flipped it upside down. So it's kind of like saying if you're driving your car at a velocity of 100 kilometers per hour. It's the same as saying in 1 hour you travel 100 kilometers, right? You didn't really change anything. You flipped your fraction around and you rephrased your sentence. You're traveling 100 kilometers per hour is the same as saying in 1 hour you travel 100 kilometers. It's the same thing, 1 hour per 100 kilometers. So we're doing the same thing with this omega. Omega is in radians per second, but I want to know how much time it takes to complete a revolution. So I'd like my units to be flipped around, to be seconds per radians, so I can then change that to seconds per revolution. And then later, because the question asks me for minutes, I can change my seconds to minutes. So that's what I'm doing here. So I'm going to change my radians to revolutions. So I'm going to put radians in the numerator, revolutions in the denominator, and 2 pi radians is 1 revolution. So if I take this number that I have, I can say 1 second times 2 pi divided by 1.8299 times 10 to the negative 3. That will give me radians, will cancel, that will give me seconds per revolution. That's my period, because period means how much time does it take to complete one cycle, which is 1 revolution. So whatever I get there, that would be my period. But then the question wants me to change it to minutes, so let's just do that right away. Instead of seconds, I want to put seconds in the denominator so that it will cancel out with the seconds. 1 minute is 60 seconds. So then I'll just divide by 60 as well. So I'll just read aloud what I'm typing on my calculator. I have 1 times 2 pi times 1, which I don't have to write times 1, and then divided by 1.08299 times 10 to the negative 3, and then in my denominator as well is 60, so times 60 in the denominator. and I get 96.695, so I'll round that to 96.7, and that's minutes. Okay, so that's my final answer here. That was a really weird way of calculating it, but I find that it's really nice to just look at the units. If you know omega, you could figure out period. You just have to flip your omega upside down. So instead of radians per second, you get seconds per radian. And then you can change it if you want radians to be in revolutions instead, because period is how long does it take to do one revolution. So you would have to change it to seconds per revolution. So really my answer is 96.7 minutes per revolution, because if we look at the units, the radians cancel out, the seconds cancel out, and we're left with minutes on top and revolutions on the bottom. But when the question says, what is the time interval required to complete one orbit? Well, one orbit is one revolution, so how much time does it take? It takes 96.7 minutes. So I don't have to put per revolution on the bottom, because that's what the question's asking for. Okay, so that was question 3. Let's move on to question 4. Okay. A train slows down as it rounds a sharp horizontal turn, slowing from 90 kilometers an hour to 50 kilometers per hour in the 15 seconds that it takes to round the bend. The radius of the curve is 150 meters. Compute the magnitude of the acceleration at the moment the train speed reaches 50 kilometers per hour. Assume it continues to slow down at this time at the same rate. All right, let's start by changing everything to proper SI units. So our initial speed, so I'm going to write V initial, is 90 kilometers per hour. Let's just change that to meters per second right away. So we want to get rid of hours, so we'll put hours on top, seconds on the bottom. 3,600 seconds is 1 hour. We want to get rid of kilometers. Instead, we want meters. 1,000 meters is 1 kilometer. So our V initial is 90 times 1,000 divided by 3,600. So we get 25 meters per second. Okay, what about our V final? Our V final is 50 kilometers per hour. And we want to change that to meters per second, so I'm going to put hours in the numerator, seconds in the denominator. There's 3,600 seconds in 1 hour. Instead of kilometers, we want meters. 1,000 meters is 1 kilometer. So I'll type that up. And I get 13.888. I'll write it out as a fraction, so I don't have all these rounding errors. 125 over 9 meters per second. Okay, it takes 15 seconds to round the bend, so that's delta t is 15 seconds. And the radius of the curve is 150 meters. Compute the magnitude of the acceleration at the moment the train speed reaches 50 kilometers per hour. Okay, so it's asking for acceleration. So remember, for all these types of questions, you always have to say, well, what type of acceleration is there? Is there a tangential acceleration? How do we know? There's a tangential acceleration if the object is speeding up or slowing down. And it is, right? The object went from 90 kilometers per hour to 50 kilometers per hour, so it's slowing down. So because of that, yes, there is a tangential acceleration. So how do we find that? Well, tangential acceleration, to calculate it, you're just using the kinematic equations. The A's in the kinematic equations are referring to the tangential acceleration. So we know V initial, we know V final, we know delta t, and we're looking for A. So we can use an equation. V final equals V initial plus A times delta t. And we can rearrange to solve for A. V final minus V initial over delta t. And just to be clear, we'll put a little t here. This is the tangential acceleration. V final is 125 over 9. V initial is 25. And delta t is 15. So now let's calculate this. 125 over 9 minus 25, and then divided by 15 is negative 0.74074 meters per second squared. Okay, so this is the acceleration that's in the tangential direction. So this means that, let's say our object, which is our train, is traveling, it's rounding a sharp horizontal turn. So it's rounding a bend, it says. So the tangential acceleration, let's say the train is moving in this direction, but it's slowing down. So it said it went from 90 kilometers per hour to 50, so it's slowing down. So in fact, the tangential direction is moving in the opposite direction of its motion. It's going this way. So that's the tangential acceleration because it's negative. Okay, so it has tangential. But what was the other type of acceleration? It was radial. Does this train have radial acceleration? Well, how do we know if something has radial acceleration? If an object is moving in a circular path, it automatically has radial acceleration. So the answer is yes. And how do we calculate the radial acceleration? Well, remember there are two equations for radial acceleration. AR equals v squared over r, or AR equals omega squared r. Those are the two equations. So we just need to know which one are we going to use. Well, the question tells us, it says, find the magnitude of the acceleration at the moment the train speed is 50 kilometers per hour. So that's the speed, that's v. So we're going to use the first equation. So AR equals v squared over r. It's the 50 kilometers per hour. We just need to change the units, but we already did. We said when v is 50 kilometers per hour, that is 125 over 9 meters per second. So I'm going to change that. So I'm going to change that to 125 over 9 squared over r, which is 150. And I'm just going to type that up. 125 over 9 squared over 150. And I get 1.2860 meters per second squared. Okay, so the question asked for the acceleration, and I found the tangential acceleration, and then we found the radial acceleration. But which is it that it's asking for? We found both. When it asks for acceleration, that means you need to find the tangential. First ask yourself, is there a tangential acceleration? If the object is speeding up or slowing down, the answer is yes. If it's moving at a constant speed, then it would be no. You also have to ask, does it have radial acceleration? If it's traveling in a circular path, the answer is yes. If it's traveling in a straight line, the answer would be no. Okay, so now we found out we have tangential and acceleration. So what do? Well, we have to add them up as vectors. So let's say, like we were saying before, our object is moving in this counterclockwise direction. Well, we said then that, let's say we're at this point in time, where the train is right here at this point. Well, because it's slowing down, the tangential acceleration would be going in the opposite direction of the velocity, so it's opposite of the motion. So this is the tangential acceleration. And the radial acceleration is going towards the center of the circular path. So this is the radial acceleration. Okay, notice that the tangent line to the circle and the radius to the line that joins the edge of the circle to the radius, those two lines are always perpendicular. So we need to find the sum of those, but we're adding them up as vectors. So when you add two things as vectors, so let's draw it again like this, AT and AR. Remember, when you add as vectors, you need the two vectors to be tip to tail. So your AT would look like this. And your resultant would be something like this. So that resultant is our total acceleration, which we just call acceleration. Okay, so our AT we know is negative 0.7074. It's pointing in the opposite direction of the velocity, that's why it's negative. And then the AR, I wrote this as T, but it should be R over here. AR is equal to 125 over 9 squared over 150, which I don't know where that went, is 1.2860 meters per second squared. So now how do you add those two up? How do you find this hypotenuse? Well, it's a right angled triangle. So to solve for A, you can really just use Pythagorean theorem. So I'll do it on the side. A squared plus B squared equals C squared. Your hypotenuse has to be your C, and your other two sides can be A and B. It doesn't matter which one's which. So my A is my AT, my B is my AR, and my C is my A. This is what I'm solving for. So when I'm solving for A, I get A is equal to AT squared plus AR squared in a square root sign, right? Because I have to square root both sides to get rid of this squared here. So I get the total acceleration, which is just A, is the square root of AT squared plus AR squared. And now I can put my numbers in. So AT, it doesn't matter whether I put the negative in or not, but if I do, I have to remember to put it in brackets so that when I square it, it becomes positive. And then I can just type all of this up on my calculator. And I get 1.48 meters per second squared. There's a couple more questions you can try, so try them on your own, see if you can get them, and the solutions are all posted in the homework. Alright, I hope all of that helps. Thanks so much for watching. See you next time.